Direct formula. So there is an algorithm, Tonelli-Shanks, that we can use here. And what it does, it's a fast way to compute the square root in n. Now, we just talked about how the case p congruent to 3 mod 4 can be handled directly. But the Tonelli-Shanks algorithm works no matter what, even if the prime is congruent to 1 or 3 mod 4, it doesn't matter. Any odd prime works for this algorithm. And this algorithm is described on the Wikipedia page here. And in this video, we're actually not going to explain why this algorithm works, but we are going to implement it in Python just by following the wiki article there. Maybe in the future we could do a video explaining why it works from a theoretical standpoint. Just to look at the article here, Tonelli-Shanks algorithm. We see it right here. Here's the web address. And we'll go through it when we implement it in Python. And then to end the talk, we'll just show a little application of where this can be used. We can use this to find points on an elliptic curve. All right, so let's begin to implement this. The first thing we should do is just to write a little function that resembles Euler's criteria. It's just a little test to determine if a given value n is a quadratic residue or not. And so why don't we call that method is quadratic residue. It'll take in the parameters n and p. If n is divisible by p, then n is like 0 in fp, right? And so 0 is a quadratic residue, and we just return true. That's kind of a trivial case. So as long as that's not true, then we can proceed, and n is co-prime to p then, and we can use Euler's criteria. We calculate n to the power of p minus 1 over 2 mod p. That's that POW function there. Notice the double slash there, that's like a floor division there, so we get an integer back. And we're just really saying if the Euler criteria value is equal to 1, then we have a quadratic residue. If it's not equal to 1, which really means it's minus 1 or p minus 1, then it's not a quadratic residue. So that's our version of Euler's criteria. So let's begin to write the Tonelli-Shanks algorithm, and it'll take two parameters, p and n. p is our odd prime that we're working with, and n is some integer that we would like to find the mod p square root of. Now, why don't we just dispense of the trivial case where n is divisible by p? Then, yes, it has a square root. The square root of 0 is 0, so we'll just return 0 in that case. So that's, from now on, in the rest of the function, we can assume that n is coprime to p, which just means it's not divisible by p. And why don't we just change the order? Instead of pn, let's change the order of the parameters to np. Now we can use Euler's criteria to tell if n is a quadratic residue or not. If n is not a quadratic residue, then we might as well stop. There's nothing else to do. So if we don't have a quadratic residue, then just print, this is the value of n is not a quadratic residue, and just return none. Otherwise, we do have a quadratic residue, and our task for this video is to, instead of just knowing that theoretically that it exists, that there's some number x whose square is n, the goal of this video is actually to write some code that is going to find that number within a reasonable amount of time too, because we want to use large primes. And we can't write a brute force search to find it. We need algorithms to hone in on the number that we're looking for. In this case, the square root, right? So we know that we have a quadratic residue n. And in the case that p is congruent to 3 mod 4, we don't really need a special Tonelli-Shanks algorithm. We can just return n to the power of p plus 1 over 4, and we'll have a square root right there and be done with it. So let's code that up. Now, like I said, the Tonelli-Shank algorithm works for primes congruent to 3 mod 4 just as well as primes congruent to 1 mod 4. But returning this power n to the p plus 1 over 4 is definitely faster. So let's do it that way. All right, so at this point in the code, p is congruent to 1 mod 4, but like I'm saying, it doesn't matter. So now we're basically following the wiki article here, just following the steps. Our first step is to take the number p minus 1, which is even, pull out all the powers of 2 we can, so we'll write it as 2 to the power of s, and then we'll have a number q right beside it, which is odd. So let's define q as p minus 1 and s to be 0, just to initialize those variables. And we'll just do a little while loop. Whenever q is divisible by 2, which will happen at least once, s is going to be incremented by 1, and q will be divided by 2 and reset. And we'll just keep doing that until q is no longer divisible by 2, and then it'll be odd. I didn't write q as odd in my comment there, I should have. And then we'll just print q and print s out. After these print statements I'm going to write are just for debugging. If you want to erase them after, you probably should. And if we look at the next part of the wiki article, we need to find a quadratic non-residue, z. And remember that half of the numbers in FP, the non-zero numbers, are residues, half are non-residues. So just doing a brute force search for a quadratic non-residue is going to be fast. It's going to happen pretty quickly. So we'll just initialize Z to be 2. We'll test if it's quadratic residue. If it is, we're going to increment by 1. And we're just going to keep going like that until we come upon a number Z which is not a quadratic residue. And that'll help us with the calculations later. And we'll just print that Z out for debugging. And now we have some variables that are going to appear in a loop, but first we need to initialize them. And we're just following the wiki article there, according to all the formulas given there. Like I said, we're not explaining why this works. That would be a good topic for a video, but let's just implement it and enjoy the results. And after those initialization variables are set up, now comes the loop. And the loop is based on whether t is 1 or not. When t is not equal to 1, we have to remain in the loop, and the loop is based on variables are set up. Now based on whether t is 1 or not. When t is not equal to 1, we have to remain in the loop and reset all of our variables that we're using here. So whenever we do a loop, why don't we just start off by printing loop. Our first step is to calculate I. What is I? I is the least power of 2 such that t to the power of 2 to the I is equal to 1. The way we can calculate successive powers of 2 of t is just by squaring it repeatedly. And we need to introduce a temporary variable for that so we don't wreck the current value of t. And I just call that temp. So while the temp is not equal to 1, we increment I and we do temp equals temp times temp mod p. And that resembles t to the power of 2 to the I. And we keep going until we get it to be equal to 1. So then we have to define these next 5 variables, b, m, c, t, and r. And I just do a little helper variable here. Power of 2 is 2 to the power of m minus I minus 1. And then we follow all the definitions in the wiki article there. B is c to the power of 2 mod p. M is just equal to I. C is b squared mod p. T is changed to t times b times b mod p. And r is r times b. So, and we're just going to print out all these values each time we loop. That'll be for debugs after we're happy that it works. And the nice thing is, after we break out of that loop, which will happen, the value of r is the square root, and we're done. So that's very nice. And that's the Tonelli-Shanks algorithm, giving us the square root of n mod p when it exists. We're done. So we should try to test this a little bit. They actually give us a little scenario here where we can try it out. We're going to take the same numbers as they have here. So we're going to try to find the square root of 5 mod 41. And when we run it, we see that we get all these intermediate values that they've talked about. And that's good. Now, one thing I want to point out is that the prime that they use there is 41, and that's a prime that's congruent to 1 mod 4, which means that the Tonelli-Shanks algorithm is really needed there. What if we used a prime that's congruent to 3 mod 4? And remember, that's the case where we have a direct formula available. So let's try 43. 43 is congruent to 3 mod 4. And when we try 5 there, as to trying to find the square root of 5 mod 43, it actually is not a quadratic residue. So Tonelli-Shanks just says, sorry, you can't do anything. So why don't we change 5 to 6? Maybe that'll work. And it does. So and we get 36. So it's kind of...
Upon the completion of this session, the learner will be able to, outcome number 1, we will understand the working of Chinese remainder theorem with an example. Let's directly dive into the topic of the day, the Chinese remainder theorem. Let me tell you the theorem first. The Chinese remainder theorem, simply CRT, is used to solve a set of different congruent equations with one variable but different moduli which are relatively prime. It means we are going to have a set of different congruent equations. It's clear that these congruent equations are different but with only one variable and different moduli. So we are going to find the value of this one variable using Chinese remainder theorem. I know things will be little bit not clear for you at this stage. Anyway, when we see some examples, you will understand this. Before that, let's have a theoretical understanding. So we have different congruent equations as mentioned in the definition, where x is congruent to a1 mod m1, x is congruent to a2 mod m2. We have n equations, x is congruent to an mod mn. If you see here, we have one variable which is x here, right? And we have a set of different congruent equations which is this. We have n different congruent equations. And if you note here, there are different moduli. This is mod m1, this is mod m2, this is mod mn. We have n different equations with different moduli, different a values, but the variable is 1. Now we are going to find the value of this single variable. Let's see what this Chinese remainder theorem states. So Chinese remainder theorem states that the above equations have a unique solution of the moduli are relatively prime. So m1, m2 up to mn, when they are relatively prime to each other, then there exists a unique solution x. I hope the theorem is clear for you. If not clear, no worries. Let's solve example number 1 and you will understand things clearly. Before diving into example number 1, what is the formula for finding this value of x? So the value of x can be x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse up to an mn mn inverse mod capital M. If you note here, few values are available on the question. a1, a2 up to an can be taken from the question, and we are required to calculate the other unknown variables including this mod m using the values that are available in this set of congruent equations. So this is the equation which is used to find the value of x. Let's see example number 1. Solve the following equations using Chinese remainder theorem. The equations are x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. How many equations are given in this question? 3 equations. So we are going to modify the formula in such a way that it is going to cater 3 different congruent equations. You can adjust the formula according to the need. Let's solve this now. We are going to have the equation like x is equal to a1 m1 m1 inverse plus a2 m2 m2 inverse plus a3 m3 m3 inverse whole mod m. Why we are stopping up to m3? Because we have 3 equations 1, 2 and 3. If you have 4 equations, then add plus a4 m4 m4 inverse mod m. So it's so simple. Since we have 3 equations mentioned in the question, our formula goes like this. Now let's see what are the given data. In order to find the given data, let's see this with the comparison. We know Chinese remainder theorem, we have different congruent equations like this. X is congruent to a1 mod m1, x is congruent to a2 mod m2, and x is congruent to a3 mod m3. Since we have 3 different equations in the question, I am stopping up to this. And what's the given data in the question? It's x is congruent to 2 mod 3, x is congruent to 3 mod 5, and x is congruent to 2 mod 7. Let's compare these two so that we can find the given data. So we know this is the equation we are going to apply, and the given data are a1 is 2, a2 is 3, and a3 is 2. So that's what we have mentioned here. A1 is 2, a2 is 3, and a3 is 2. Then what are all the other given data? Small m1, small m2, and small m3. So small m1 is 3, small m2 is 5, and small m3 is 7. So these are the given information. Please be noted that there exists a unique solution only when small m1, small m2 and small m3 are relatively prime. In other words, GCD of small m1, small m2 and small m3 is 1. Since there is no common factor except 1 that can divide 3, 5 and 7, we can say 3, 5 and 7 are relatively prime. Alright, when we see this equation, we can say a1, a2, a3 as given in the question, but there is no small m1 here. We have capital M1 inverse, capital M2 inverse, and capital M3 inverse. In other words, these are all small m1, m2, m3, these are all big m1, m2, m3. So we are required to find capital M1, capital M2, capital M3, and capital M1 inverse, capital M2 inverse, and capital M3 inverse. Also, we are required to find the value of capital M, which is this. So we will find all these values. Once all these values are known, we know a1, a2, a3 are already given in the question. We will just substitute the values and evaluate this expression so that we will get the value of x now. So let's start doing this now. So we know the given data are a1, a2, a3, small m1, small m2, small m3. Let's find capital M1, capital M2, capital M3 and their corresponding inverse, also capital M. To find capital M, it's so simple, it's the product of all these small m's. So we have small m1, small m2, small m3, right? So capital M is the product of small m1, small m2 and small m3. So when we substitute this, we get capital M is equal to 3 into 5 into 7, which is equal to 105. So we found the value of capital M, which is 105 here. We are done with finding capital M. Let's now move on to find capital M1, capital M2 and capital M3. So let's navigate to finding capital M1, capital M2 and capital M3. How to deal with this? So we are going to find 3 values, capital M1, capital M2 and capital M3. So the formula is capital M1 is equal to capital M upon small m1. That is what we have found here, capital M upon small m1. Similarly, capital M2 is equal to capital M upon small m2 and capital M3 is equal to capital M upon small m3. We know the values of capital M and all small m values, right? we will just substitute it here. So when we simplify this, we get capital M1 as 35 and capital M2 as 21. Why 21? Because capital M is 105 and small m2 is 5, which is this. So we get capital M2 as 21 and capital M3 as 105 upon 7. Why 7? Because to 15 capital M3, which is 35, 20. Now we inverse are going to find the multiplier is multiplied. Similarly, capital M2 is multiplied by capital M2 inverse will give 1 under mod small m2. Similarly, capital M3 is multiplied by capital M3 inverse will give 1 under mod M3, which is small m3, which is this. So we will substitute the values what we have found. So let's focus on finding capital M1 inverse. So we substitute M1 to be 35 because that's what we have found it in the previous step. So we have 35 is multiplied by capital M1 inverse will give 1 mod 3. Why 1 mod 3? Because small m1 is 3. Now you can go for extended Euclidean algorithm to find the multiplicative inverse, or you can start applying from the values 1, 2, 3 till you get the final result. So let's start with 1. When capital M1 inverse is 1, 35 into 1 is 35. Then 35 when it is divided by 3, are you getting 1 as the remainder? 35 when it is divided by 3, you get 2 as the remainder. So M1 inverse is not 1. Let's try 2. So 35 into 2 is 70. 70 when it is divided by 3, we get 1 as the remainder. So we have M1 inverse as 2. We easily found it out because all these values are small numbers, so I am not going for extended Euclidean algorithm for solving this. If the numbers are big, I want you to find the multiplicative inverse using extended Euclidean algorithm. If you are not sure about this extended Euclidean algorithm for finding the multiplicative inverse, I request you to watch my previous lectures. We are done with finding capital M1 inverse. Let's now move on to capital M2 inverse. So we know capital M2 is multiplied by capital M2 inverse will give 1 mod small m2. So we will substitute the values here. Now let's start applying 1 to capital M2 inverse. If we use M2 inverse as 1, 21 into 1 is 21. 21 when it is divided by 5, we get 1 as the remainder. Yes, it's perfect. So we know capital M2 inverse is 1. And we will move on to the next step, finding capital M3 inverse. We will apply the value capital M3 is equal to 15, which is this. Now 15 is multiplied by what? We will get 1 as the remainder when it is divided by 7. Let's apply 1. So 15 when it is divided by 7, we get 1 as the remainder. So M3 inverse is also 1 in this case. So we have found out the values of capital M1 inverse, capital M2 inverse and capital M3 inverse. We will substitute the values. So now we got all the values that are required to find the value of. So it's clear that we have expression M1 inverse plus A2 inverse. I'm gonna take this and place it expression 2 is 105 here. So when you evaluate this, you get 23 as the remainder. So finally, we got the value of x to be 23. So let's take it by 3 mod 5. So 23 when it is divided by 5, are you getting 3? Yes, 5 4 times 20. Equation 7. We found out the also having the different congruent equations under